SealedGRID is an European project coordinated by a consortium of 4 academic and industrial partners from Spain, Romania and Greece. It focuses on the protection of the smart grid, which is a vital economic and social infrastructure that is exposed to many security and privacy issues. The objective is to develop a platform that provides security features to legacy equipment, while at the same time all the shareholders can use it to provide new tools. This platform integrates different cybersecurity solutions, ranging from key management or authorization policies to innovative technologies such as the blockchain. One of the main requirements for the success of this project is the active collaboration between all partners by means of secondments, research articles, conferences and meetings. In this video, we will show the different solutions that are being implemented in SealedGRID and how they help to ensure the security of the smart grid.
Attribute-based access control goes beyond role-based access control while addressing many of its limitations. Attribute-based access control uses fine-grained access control and considering a number of user attributes, including location, time of the request, and even the context. So attribute-based access control solutions generally use Boolean logic, and this lets these type of solutions effectively define access policy without using roles. So for example, a company can define a group which is called, for instance, management, and allow only its members to access certain files. So with role-based access control, this would require coding access rules about those files for every role, and the difference in maintenance between these two approaches adds up quickly. We are working towards a flexible hybrid role-based access control and attribute-based access control while using standard-based approaches like XACML, the use of policy decision points and policy enforcement points that satisfies requirements of critical infrastructure protection, as well as being interoperable with the new secure smart grid devices that are being designed by our partners. Okay, so why is it important to implement an authorization policy? That's because security interoperability is one of the most challenging research areas within the field of critical infrastructure, as revealed by international organizations such as the NIST or the IEEE. In this context, diverse devices like sensors or meters, actuators, and various communication systems such as Wi-Fi, Zigbee or 4G cellular, as well as different domains, have to live together in a unified ecosystem to lead critical actions. So the design of secure authorization and interoperability mechanisms is a complex task. Solutions, identity and access management solutions vary in their approach to authorization, with the preferred method, or what we call the legacy method, often being role-based access control. Now, role-based access control involves defining the roles a company needs, specifying permissions per roles, and then matching users to roles. So although logical, role-based access control has some limitations. First, whenever a company adds a resource, access rights for that resource have to be defined per role, which makes role-based access control difficult to maintain. This problem is compounded because companies often create many very detailed roles, each differing by access rights to only 1 or 2 resources. So as a result of the great number of technical details that are involved, IT is usually responsible for authorization in companies that choose role-based access control. This makes management dependent on IT when implementing important business decisions, and think about what happens when hundreds or thousands of smart grid nodes are involved.
Another novelty in the SealedGRID project is using the blockchain. Blockchain can be used for 2 things. We can create a large-scale secure authentication system for smart grid networks without the need of a trusted third party, which is the central element of the SealedGRID key management mechanism, built on top of the PGP Web of Trust. For example, we can have a permissioned blockchain network between Alice, Bob, and Carol. Carol sets this up using a blockchain platform that assigns permissions, can connect to the network, can transact to the network, can issue on the network to public keys. Carol configures the network so that her key management public key can use assets on the network. She invites Alice and Bob to join. Both of them are okay with Carol's ability to issue assets on the chain. All of them have a pair of private and public keys. Carol submits a signed transaction that generates, for instance, 10 units of an X resource, let's say, for example, energy. The nodes on the network consider this transaction valid since her public key is permissioned appropriately. Carol then transfers these newly generated units of X to Alice, which brings us to Alice having 10 units of X. Using blockchain, the keying of each node that is built locally can be stored on the blockchain and replicated within the network. Therefore, nodes have the option to decide whom to interact with and why to place trust on each of the agents independently, as the SealedGRID key management specifies. But they also have the added advantage of being able to access information from the nodes via blockchain, paving the way for a future more flexible SealedGRID key management implementation. Another benefit of blockchain is the ability to generate smart contracts. Smart contracts are basically contracts with clauses that are digital, enabling transactions of assets when a certain clause from the contract is fulfilled. Local energy markets, on which consumers and prosumers can trade locally, produce the energy directly with their community, balance generation and consumption locally in a decentralized approach. Our approach is based on a private blockchain, which underlines the decentralized nature of local energy markets. Thus, we can provide energy prosumers and consumers with a decentralized market platform for trading local energy generation without the need of a central intermediary.
Masker provides a privacy-preserving aggregation solution for the smart grid. Each smart meter participating in the architecture shares cryptographically generated pseudorandom values with the utility. These values act as masks and obfuscate the real consumption readings of the smart meter. This way, an intermediate aggregator can provide the utility with an aggregated consumption by several smart meters without knowing the real energy consumption. The utility subtracts the used mask from the received total sum, resulting in the real combined consumption of all relevant smart meters. The only entity that has access to the real energy consumption value is the smart meter itself. All the performed sensitive computations are protected by utilizing a trust execution environment which stores data and executes the crucial operations. By utilizing Masker in SealedGRID, we achieve a privacy-preserving aggregation solution of energy consumptions that facilitates demand response, which is highly trusted and scalable, imposing low computation overhead. Besides the benefits of such an endeavor, the smart grid will be exposed to security threats inherited from the information and communications technology sector, while privacy issues and new vulnerabilities related to specific characteristics of the smart grid infrastructure will emerge. The smart grid nodes will be accessible by customers, creating a fertile field for malicious users that may intercept personal information or alter energy measurements and costs. Thus, the customer's privacy should be protected.
Trust is important in order to ensure that only legit and not malicious entities handle the data that is transmitted in the smart grid. Inclusion of untrusted entities in the smart grid could result in data leaks or even disruption of network operations. SOMA is the underlying key management scheme utilized by SealedGRID to build a trust relationship combining public infrastructure and web of trust concepts. In simple terms, this is accomplished by making use of individual certificates assigned to the nodes of the smart grid, whether they are simple smart meters or aggregators with increased responsibilities. Each one of these certificates gradually accumulates signatures from endorsers across the network, thus building trust relationships.
devices and operators within the SealedGRID architecture are given with certificates and permissions to perform a certain set of operations within the grid according to an access control policy. This policy defines the rules and conditions that must be fulfilled when a new action is requested. However, the decision whether to grant access to a certain resource or not must be also subject to the security state of the network in that precise moment. And at this point, context awareness is very important. The context awareness mechanism that we are currently developing is present in every component of SealedGRID, ranging from the smart meters to the utility. The aim is to provide information in real time about the security state of all devices. For example, measuring variables like the number of connections that are established with all the devices, or for example, the usage of computational resources. So then we can compare the current value with the value in normal conditions. So maybe those deviations that appear are caused by a potential threat. Once this information has been gathered from an individual device, we can correlate this information with the information from other devices within the network using opinion dynamics. This algorithm permits to gather the information which is distributed across the entire infrastructure and then identify potential areas which are subject to an attack. And then at the same time, we can provide suitable information to the authorization component, as we said before. So now we can perform a decision to grant access to a resource or not only taking into consideration the security policy itself, but also the security state of the network in that point. The impact of SealedGRID will be evident in the research area of critical infrastructure protection, and it will also bring benefits for both smart grid operators and customers.
Communication between the network's entities will be faster, while at the same time the consumers can be rest assured that their personal data, which is communicated throughout the network, is secured.
With SealedGRID, we are taking a step further by proposing an architecture that is able to ensure the security of all components at all times, but it is also able to protect the privacy of customers, which we believe it is very important for the adoption of these technologies in society nowadays.
We provide the future in secure smart grid.